Pues bienvenidos todos a una nueva edición del Madrid Machine Learning Meetup. Hoy estamos aquí con Pablo, que es Principal Engineer en Wave, una de las empresas robóticas más potentes del mundo, y vamos a revisar un poco el trabajo de esta empresa, que yo creo que es puntero, ¿no? Y bueno, Pablo, yo creo que no podría ser persona más indicada para venir a hablarnos de esto. Pablo hizo su tesis en la Universidad de Alcalá, ha hecho una carrera investigadora brillante, principalmente en Reino Unido, pero también en Estados Unidos y en Francia. Ha participado activamente en la comunidad investigadora, sobre todo en el mundo del SLAM, Simultaneous Localization and Mapping, y hoy tenemos la suerte de tenerlo aquí, así que un aplauso y muchas gracias por venir, Pablo.
Bueno, muchas gracias por la invitación, también gracias por los que habéis asistido, que yo entiendo que en estos días de calor en Madrid, además hoy que juega el Madrid en el Mundial de Clubes y demás, pues bueno, es complicado venir aquí a una charla de vehículos autónomos, entonces gracias por asistir. Y bueno, también por otro lado, yo soy de Madrid también, lo que pasa es que vivo mucho tiempo fuera, entonces pues me hace mucha ilusión. Llevo como camino de 3 años otra vez en Madrid y bueno, pues me hace ilusión poder venir a estos meetups y poder hablar un poco de lo que estoy haciendo, ¿no? Y poder hacer un poco de networking. Voy a empezar la charla, la voy a hacer en inglés. ¿Algún problema o no?
No, por favor, porque de hecho sé que hay alguna gente en el público que no entiende muy bien el español, así que...
Perfecto. Si alguno os da vergüenza preguntar en inglés o no lo domináis, me podéis preguntar en castellano también. Okay. Okay. So let's start by what is autonomous driving? Who knows about the 5 levels in autonomous driving? 2, 3, okay, well, half of the audience, that's good. So level 0 is no automation. We can have some warnings, but you know the driver is in control. Then we have level 1, we have some driver assistance, but the driver is still in control. So maybe we have some driver assistance about the steering or speed, but you know the driver eyes on, hands on. Then level 2 is what we call ADAS, which is partial automation, which is a combination of level 1 driver assistance systems, which, you know, the driver is not expected to be with the hands on the wheel the whole time, but, you know, it needs to be ready to intervene if something happens and take control of the car. Then level 3, which is what we call conditional automation. So this is, the car is almost automated, but, you know, the driver is also can intervene, and it's automation with some conditions about the speeds, ODDs, environments, and so forth and so on. Level 4 is what we call more the robotaxis, for example, what Waymo is doing in California or some other cities in the US, which this is kind of high automation, but in geofence environments, so just in particular cities and under some conditions of speed as well. And level 5 is the dream, so it's a complete automation, no geofence environment, just take me to any kind of destination, any kind of environment. But, you know, that's where we're heading, but we're still a bit far from that. Why do we want autonomous driving? So there are 3 main reasons. The first one is safety. Most of the car crashes are due to human error, and, you know, there are already some studies that show like ADAS or autonomous vehicles, they reduce the number of car crashes compared to human driving. Mobility for all, like autonomous vehicle can give independence to people who cannot drive. You can order a car by your phone, the car shows up, there's no driver, you can go to another point, and you know, it makes it easier. And then also economic efficiency. You can operate 24/7 without brakes. Okay, why do we think at Wave in terms of autonomous driving? We think like autonomous driving is an artificial intelligence problem, and I'm going to explain why. This is a video from central London. I'm going to talk later about when Wave started, and it started in Cambridge and then moved to London. But basically, we have lots of experience testing the cars in London. London, the traffic is chaotic, so you have pedestrian, vans, cars, cyclists, buses, and decision making is very difficult. So why do we think autonomous driving is an AI problem? Because those problems where decision making is so complex, data-driven approaches or AI approaches make lots of sense, that your system can learn end to end. I don't know if it's my, or maybe I will use the.
Let's turn it on. Turn it on.
Yeah, thank you. So yeah, just let me press play. You could see like the scene is very complex. Now we have this van going in. And this is the prediction of the waves model. This is kind of like the prediction of the next 3 seconds where the vehicle should go. So, you know, autonomous driving decision making is very complex. So data-driven approaches make lots of sense. Also, at the same time, we have seen in many other tasks that AI is advancing quite a lot and already surpassing humans at many tasks. Like, for example, handwriting recognition, language understanding, and speech recognition, reading comprehension. I'm sure many of you these days use Copilot or Cursor to help you programming. So, you know, that's making lots of progress. So we think like autonomous driving is kind of the next frontier where AI will surpass humans. In terms of AI, autonomous vehicles, there are like 2 approaches. One is the what we call AV 1.0. Okay. Then. Okay. So one thing that I wanted to highlight is in AV 1.0, sometimes it's easier to debug things because everything is a bit more modular and you can have a bit more observability. One of the challenges, but also when you have a corner case that you want to fix, you need to touch kind of lots of lines of code and then test many test cases, and you know, it's become difficult to add new capabilities to the stack. In the case of AV 2.0, that's easier because when you have a problem, you just need to throw more data and train with more data, and then you get that problem solved. But also because of the neural network, sometimes you don't have as much observability, and sometimes debugging also becomes a bit more challenging. But you can generalize faster with AV 2.0. Now to give an idea, I mean an overview of the company. So Wave's mission is to reimagine autonomous mobility with embodied intelligence and has been all in end-to-end deep learning for driving since the company was founded. The company was founded in Cambridge in 2017. Then in 2018, they show like end-to-end deep learning driving policy. In 2020, after the COVID, the company expanded operations to London. 2022, they demonstrated like generalization to new vehicles in different UK cities. 2023, they released the first language action model for driving and generative AI for simulation. And this year, 2025, we have done new expansion to US, Germany, and Japan. So nowadays, Wave has offices in these 4 countries. And the company is not a startup anymore. I call it a scale-up. So now we have about 600 people across the different locations. And I think the plans is at the end of the year will be like around 1,000. So yeah, I'm spending lots of time, as I told Thiago, doing interviews these weeks. Let me show you an example. Yeah, I'm going to show you a video of the Wave AI driver. So this is a video that the company released a couple of weeks ago that shows a bit kind of the generalization experiments across UK, US, Germany, and Japan. So this is just a single model that has been trained with data from all these different countries, and the model is able to generalize to different geographies. So this is London, San Francisco, Stuttgart in Germany, that's where we have the office, and Japan in Tokyo. And yet the good thing about AV 2.0 and the embodied AI approach of Wave is that the approach can generalize very quickly to new locations. So we want to be the first company that generalizes AV to more than 100 cities. And I'm looking forward to testing Wave cars in Spain, hopefully soon. And you could see also it's like urban, villages, suburban, nighttime as well. Okay, so now I'm going to explain a little bit more the magic behind all of this and what it takes to, for this AI system to generalize to different environments. Data set is important. So as we have seen in many other tasks in computer vision or AI or neural large language models, we have seen that the top performer models, like the order of parameters are like, kind of at the order of billion of parameters. So the same applies to autonomous driving. You need a model with lots of parameters. But also, big models also need to match, and you need also large amount of data in order to train those models correctly. These are like some tables from a reference paper that I don't remember the reference. But what we can see is sometimes like big models, they plateau in terms of the loss, and then the loss increases when you increase the number of parameters. But that's also, you need more data for the loss to decrease. So the same applies for autonomous driving. So we have said that for AV that generalizes across different geographies, we need big model and we need lots of data. But life is not that simple, and there are many other problems. Safety. For example, one of the organizers here asked me what happens in terms of safety and regulations if there is an accident. I don't know. I'm an engineer, so I don't know that answer, but it's it's an important question. Connectivity. You need connectivity from the vehicle connected to the internet to have access to the GNSS and being able to upload the data. Trust. People that jump into these cars, they need to trust that it's safe. And also the people around these cars, they need to trust, like when they see an autonomous vehicle, like they don't panic. But also this is a robot with compute, right? So we have limited on vehicle compute. We cannot use like one of these massive GPUs on a commercial platform. Is to make it run in a limited compute. Able to react to those scenarios. Kind of the central problem that we're trying to solve here is minimize the interventions per kilometer or minimize the number of critical interventions per kilometer. But that, you have many constraints, right? So that's the small print. So this is subject to the model that needs to run at a certain frequency on the vehicle. The model needs to have full observability of all objects, traveling up to distance. The model needs to have temporal context. The solution doesn't need to cost runway. Must try the solution. No maps available. Limited connections. Blah blah blah. Lots of problems that you can think of. Like, let's talk about Wave's approach for AV 2.0. Wave we use for the model, we use depends on the vehicle platform, but at least 5 cameras in the car. Forward cameras, rear cameras, side cameras. Why? Because images, basically, picture worth 1,000 words. Like, images provide lots of context, lots of information, lots of about the surroundings of the car, but also, it's several million bytes. More if you need to consider temporal context and spatial context. Kind of tensor, but a spatio-temporal tensor with images in the surroundings of the car. Over time, we can capture also different time intervals. We can also use high resolution because we need to detect objects that are far away. So cameras give us lots of information, but also there is lots of bytes. So this is like some maths, like for example, if we use time, so 20 frames, we have 6 cameras per frame. Was 23 gigabytes, which is roughly the compressed size of Wikipedia. So this is lots of information for just 20 seconds of video data. And more in the number of tokens for some models, like this is like. So yeah, the question is, how do you officially can encode high resolution video data into learn how to drive and what it is and geography. So the first one is edge filtering and data selection. So this is more or less kind of what the classical approach is, like how do you collect data for autonomous driving. At the end of the day, this kind of approach is more like behavioral cloning. For example, you collect lots of expert data from actual drivers. You collect many of them, you train your model, you train your model in the real world. You have some failures, the safety operators come up with some annotations, you retrain, and that works. But the problem is data. And what happens here is that also means money because you need to have the vehicle fleet operating almost 24/7. You need to have bandwidth to cloud, which may be also expensive. So this is an option, but it's a very expensive one. So what can we do about it? There are some papers also like this one from Microsoft Research that says textbooks are all you need. So this is more like you don't need all the data to train your model. You need to focus on it. Adaptation and generalization. So this is some experiments that we did when we first tried to generalize a model that was trained with driving data in the UK, and we tested for first time in the US. So we see this is this is a gap compared to the UK performance. So we had the first zero-shot experiment, and the performance wasn't great. Then we did 100 hours of data, and we improved performance 5x. And then we added 500 hours of data, and we improved performance 40x. So almost after 500 hours of data in the US, we got almost parity in terms of performance between the UK and the US. So that kind of says okay, you need some amount of data to generalize to a new country, but it's not that much. And I'm gonna play here Well, I mean, these are examples that basically videos that show the differences between what it could be driving conditions in the UK, London, mostly urban, to the US, where you have at least, you will have like 3 lanes. Also an important bit that you haven't told me, like the site where you drive is different between UK and the US, but the model is running that. So, and this is more like, yeah, more in terms of generalization. This is more like some particular driving behaviors, what it took to match the performance between the UK and the US model. So for example, this is the stop sign. You could see like almost 500 hours. We got at almost parity. Right turn on red, unprotected left turn, and this is on ramp. This of course depends on how you sample your data, but different driving behaviors, you know, you may need to add more data to generalize, but roughly 500 hours, you get enough data to match performance in the UK. Also, let's stop this. Yeah, what we have seen also is that training with data from the different geographies also helps with model accuracy and improves generalization. So, not sure if you can see it here very well. So this is blue, is just with the initial data, and then red here is additional data from the UK and US that you consider in training, and you could see like the training steps, and the error gets reduced when you use data from different geographies. So it helps you also to generalize and training. And this was like maybe not even two months ago. So Wave now has offices in Germany. So this is one video of the generalization experiment in Stuttgart. So this is like the motorway. This is kind of a bit foggy, a bit rainy, and yeah, the model now is able to drive in Germany with no problems. Okay, let me see. Oh, because now I lost the full screen. Slideshow. Okay, I think I lost the full screen. I don't know how, but let's talk about evaluation and safety. So how does it work? So this is, like we have here, like in green is when we have an autonomous vehicle. Green is that the model is in control, the model is working correctly, but sometimes we need to provide annotations for corrective actions when something is not working correctly. So this is the red here. So the red is each vehicle has a safety operator, and then the safety operator, he's not touching the steering wheel unless he needs to intervene, he or she needs to intervene. So when this happens, the safety driver takes over control, and then we have data annotation that says, okay, this is a corrective action, this is something that we need to consider for training and consideration to improve the model. However, this is a huge effort because you need like lots of kilometers, lots of data to get enough corrective action. So it's a noisy signal, it's expensive, it's difficult to cover all the long tail of corner cases, fragile, and also it's difficult to test dangerous corner cases like crashes. So what can we do instead? So we can focus more on offline methods. Offline methods, I'll tell you a little bit more about it, more like simulation or generative AI. So with offline methods, basically, you have the predictions coming from the model, but also you can control some of the the behavior of the agents and the car to introduce corner cases and come up with new corrective actions. So yeah, this is basically kind of the long tail of corner cases. So this is more like the real world data that you can collect, or we collect at Wave. Like most of the data, you say like, oh, it's easy, it's not problematic, the vehicle knows how to drive. The problem is here, is in the long tail of corner cases, like crashes, or if a deer shows up in the middle of the night and is gonna crash with the vehicle, those kind of things. So what can we do to reduce the gap between this and this? This is where we want to be. So this is by means of offline simulation methods or generative AI that we can generate new driving situation and use both at Wave. Neural rendering is you can create neural views, synthesize new views like Gaussian splatting or nerves, just kind of to do like closed loop simulation. So what Wave has done in this area, so like two kind of breakthroughs. The first one is AI explainability, which is Lingo, which is a language model for explainability. So basically, with this, you can write a text, some prompts, and you can ask the vehicle questions, and then the vehicle will tell you, okay, like, you know, I'm stopped here because there is a car in front of me and it's raining, da-da-da. You can also, I'll show it in the next screen, you can also, based on text, you can condition new image views. And then Gaia 2 is the Waves world model. So this is a generative AI world model where you can synthesize new data based on text, based on conditioning agents and weather, things like that. So this, yeah, all these images here, this is synthetically generated by Gaia 2. So you could see that, you know, you can generate different scenarios. We can condition that in terms, we could say like, oh, we want rainy weather or sunny weather. We want like motorbikes. Or you can condition on the agents as well. And this is for Lingo. As I said, you know, we can input text and video, and then the Lingo model what's happening here. So you can have kind of a conversation with your car. You know, here is telling you I'm still stopped here, I miss the traffic, accelerating from a stop, following the lead vehicle. So that's in a way, this is also important for the user, for the people using the car, because at least, you know, the car can explain what is happening, or I mean, the model can explain what is happening and the decision that the model is making. This is more like, yeah, language prompted driving that, you know, we could specify text prompts and video input. So we could say like user is stopping behind the bus, and we can generate these synthetic actions as well. And now I think let's go to, yeah. So at Wave we are also working on what we call the Wave Foundation model, which is kind of the main brain of the driving model that we have. This foundation model consumes several inputs: sensors, camera, radar, GPS, telematics, synthetic video, driving videos, language, segmentation, traffic data. So this is all that we feed into the model for training. Then we train this model, and then you know, the outputs of this model is driving tasks, robot control, language understanding, perception simulation. But also eventually we want to use this model for, this is an autonomy model. It's not just for driving cars, right? So this is any autonomy model for robotic applications as well. So eventually we want to use it for warehouse robots, humanoids, drones, bipeds, and quadrupeds. So that's kind of a foundation model around autonomy. That's what we are aiming to build. Some of the engineering frontier. So here we have talked mainly about machine learning. This is a machine learning Madrid meetup, so that's okay that I talk about it. But machine learning is a very small piece of the cake. So machine learning, the problem is just 10%, and everything else is 90%. And I'm going to show you some of the challenges around engineering that we have. We have lots of challenges, more than what you can see here. The first one, some example, is how do we ensure a fleet of hundreds of vehicles is running reliably, and more when you have offices in different continents. How do you schedule like 100 of vehicles? How do you run your model in an NVIDIA Orin platform that is more resource constrained? How do you convert the output of the model, and what's the right representation into a signal that can be used for driving the car? How do you visualize the results? Online observability. How do you add online observability to understand what's happening in the model and in the car when you have a problem to identify the root cause? So anyway, I'm not going to bother you with all the engineering problems, but autonomous driving is not just the machine learning bit. It's like about creating robotic systems that work. Language world models and offline simulation are key components, and they're supercharging AV 2.0. And foundation models will help to unlock the full potential of intelligent robots. That's kind of what we are working at Wave at the moment. And as I said before, I'm spending lots of my time doing interviews, so we are hiring a lot, different locations, London, Sunnyvale in the US, Germany, Tokyo, and also Vancouver as well. So if you are interested, also, if it happens that you go to London and you want to go for a demo ride, let me know in case I'm there. I can try to prepare a demo for anyone that wants to do it.
There's actually Wave cars actually running automatically in London.
Yeah, not yet on commercial operations, but for development and testing purposes, yes. But they have a safety operator. It's not allowed yet to, without a safety operator in the UK. But also, big announcement came actually last week for 2027, like a collaboration between the UK government, Wave, and Uber. So the goal is like in 2027 that you can order a robot taxi in London through Uber with Wave's technology. So, 2027 is around the corner. But if it happens that you go to London before that, let me know, and maybe you can go on a demo ride.
Okay, I have a technical question. What's your opinion on video diffusion models as world models? Current video diffusion models. Well, I don't know about the previous 3 months. We have been seeing a lot of papers where they try to see, to compare video diffusion models, trying to predict what will happen next when you have the actual videos of what is going to happen next, and usually they doesn't match very much, and specifically when it comes to physically complex situations like things crashing into each other or liquids spilling or something like that. In these kind of things, there are some works that say that may not be a world model, like video diffusion model, but I don't know. What's your opinion on that?
That's a good question. I may not know all the details, mainly because the area where I'm working at the moment, it's a team working on sensor calibration and fusion. Estimation. Gaia 2 that I said, there's the archive paper, so you look for it, you'll find the details. They use some video diffusion as part of the model. I don't know the limitations at the moment. I know some corner cases or crashes or for safety, we can use Gaia 2 to generate those kind of video events. But potentially there could be some limitations, but yeah, I'm not super familiar with that.
Okay, I will read the question. Thank you.
I also have a question. So what are the challenges in this sensor fusion with such a machine, right? Like an autonomous vehicle?
Yeah, I guess, one big challenge, you work in mixed reality, so I'm sure you know that calibration is a massive headache. So sensor calibration is also a headache for this kind of systems. So at the end of the day, a calibration system running to produce observability of what's happening within the car. But also you need to have very good characterization of the model and the driving model in terms of the calibration parameters, because sometimes, because you have the neural network and everything is kind of tightly coupled, sometimes it's difficult to find the root cause of when the car is not working correctly. Is it because of the model, control, calibration? And not only in autonomous driving, I work in many robotics fields, people blame calibration as the first thing, like, oh, the sensors are not well calibrated. So, but jokes aside, yeah, I think like what is very important is to have reliable sensor fusion and state estimation that can help you with the observability of what's happening within the car and know how to correlate the model performance with the state estimation variables.
And since with driving, you have to drive well, you have to not only understand your car and what you do, you have to also understand what other drivers do. Like for example, I'm going like on a street and there is like a parking lot on the side. I can see that some guy is like trying to back up, and instead of braking, for example, in my lane, I can change lane or something like that. Or someone is like, please let me merge, or like these signs that drivers can give to each other. How do these models understand them, and do they take into account behavior of all the cars that it can see around itself?
Yeah, I mean, in a way, like the models learn from the data that you use during training. So you can imagine the fleet running 24/7 in different countries and in different cities. And in this case,
But this also in many cases depends on like driving style of particular people. What is going like to be the perfect driving style for an autonomous vehicle? Because like some people will be more kind, they will let people merge, for example, if they ask them to. Some people will and I will go and then you go. And what is there anything about like perfect driving style for an autonomous vehicle?
no, I wouldn't say like it's perfect driving style. I think it depends. Like, for example, now I haven't been here to an autonomous vehicle ride. One person. Where did you go? Waymo. So I never been to Waymo, but for example, what some people have told me that have tried Wave and Waymo. Drivers, but then the model can also learn kind of more personalization style. So you can kind of configure your training and say, okay, I want a bit more aggressive driving style, or more relaxed, more cautious. So the idea is like these are things that you could incorporate into the model with additional training data. But then at the end of the day, I think what we will see is that you can choose what kind of autonomous driving style you want as an user.
Yeah, I'm interested in like how you generate or and collect the ground truth, because for like a regular situation, like I don't know, you have to stop on the red. Okay, it's understand, yeah, or you can collect it with regular drivers or etc. But you mentioned the edge cases, for example, where you mostly have to generate this data, not collect, because it's like this. Yeah, but how you like explain to model, let's say, these ground truths, like what to do in these cases? Because sometimes, in most cases, even you don't know what to do in this situation. Like, put I don't know, accelerate to go, not to crash, or stop, not to crash. I mean, it's a lot of cases, and yeah, maybe to decide like crash a little bit or crash another car, but with small damage, or let another car to crash to you. Like, how to generate the correct ground truth for these cases.
I mean, it's kind of the supervision that the model needs. So you have lots of driving data, and then you have some annotations like this is good, this is bad. But kind of what matters is the signal that you use for supervision. At the end of the day, what the model predicts is a driving plan. So it's a prediction. I think it's a trajectory for the next 3 seconds. And then what we use for supervision, that's more where kind of the responsibilities of my team are there, like to generate with sensor vision with a SLAM, to generate good odometry or good SLAM trajectories that you can use during model training.